Professor Dave again. Let's get diagonal.
He knows a lot about all kinds of stuff. Professor Dave explains.
Now that we have learned about eigenvalues and eigenvectors, it's time to learn about their applications. So let's start by learning about something called diagonalization. Diagonalization involves taking a matrix and writing it as a product of matrices, one of which only has values along the diagonal. For example, if we have matrix A, we will write it as x, d, x inverse, where D is a diagonal matrix. If we move the x matrices to the other side, we see that x inverse AX equals D. The X matrix is said to diagonalize A because multiplying A in this way gives us the diagonal matrix D. This process only works for matrices that have unique eigenvalues, or if there are duplicate eigenvalues, then there must exist linearly independent eigenvectors for the duplicate values. The reason for this is that the diagonal matrix D is simply made up of the eigenvalues of A, while the matrix X is made up of the eigenvectors. So fortunately, once we know the eigenvalues and eigenvectors of a matrix, the diagonalization process is easy. Let's assume an n by n matrix A, which has eigenvalues lambda 1, lambda 2 to lambda n. Then the diagonal matrix D is just those eigenvalues placed along the diagonal, with zeros for all the off-diagonal elements. Now if x1, x2 to xn are the eigenvectors for those eigenvalues, the matrix X will have columns made up of those vectors in the same order as the eigenvalues, going down the diagonal, x1, x2 to xn. It's important to note that while we can place the eigenvalues and eigenvectors in any order we want once we find them, we must remain consistent in how we order them in these matrices. The first column of the X matrix must be the eigenvector associated with the eigenvalue in the first term for the diagonal of D. Same with the second column of X and the second term for the diagonal of D, and so on. Let's look at an example. Consider the matrix A with entries -3, -4, 5, 6. We must first find the eigenvalues, which means we must solve for the values of lambda that satisfy this expression, where the determinant of A minus lambda I equals 0. Taking this determinant, we get -3 minus lambda times 6 minus lambda minus -4 times 5 equals 0. Foiling these binomials, we get -18 plus 3 lambda minus 6 lambda plus lambda squared plus 20 equals 0, which when simplified gives us lambda squared minus 3 lambda plus 2 equals 0. Now by factoring this, we see that lambda minus 1 times lambda minus 2 equals 0, which means our solutions and eigenvalues are lambda equals 1 and lambda equals 2. Now to find the eigenvectors, we will plug in these values of lambda into the equation A minus lambda I times x equals 0, and solve for a possible vector x. Starting with lambda equals 1, our matrix A minus lambda I becomes -4, -4, 5, 5. The top row ends up telling us that -4x1 minus 4x2 equals 0. Dividing by -4, we get x1 plus x2 equals 0, or simply x1 equals -x2. We don't have to worry about the second row here because it ends up giving us the same thing. We will choose x2 equals 1, which means x1 is equal to -1. So our eigenvector for lambda equals 1 is -1, 1. Now we will plug in lambda equals 2. Our matrix A minus lambda I becomes -5, -4, 5, 4. Both rows will again give the same result, but looking at the top row, we get -5x1 minus 4x2 equals 0. Solving for x1, we get x1 equals -4/5 x2. Choosing x2 equals 1, we get x1 equals -4/5, making our eigenvector for lambda equals 2 equal to -4/5, 1. Now that we have all of our eigenvalues and eigenvectors, we can write out the diagonal matrix D and the matrix X. D will simply be the eigenvalues along the diagonal. D equals 1, 0, 0, 2. X will have the eigenvectors as columns, but now that we have chosen an order for the eigenvalues, we must keep that order in mind. The eigenvector for lambda equals 1 must be our first column, while the eigenvector for lambda equals 2 will be our second, making our matrix X equal -1, -4/5, 1, 1. We have obtained the main matrices for diagonalizing the matrix A. The only remaining piece is the inverse of X. Since X is a 2 by 2 matrix, we simply swap the top left and bottom right elements, multiply the off-diagonal elements by -1, and divide the whole matrix by the determinant. The determinant will be -1 times 1 minus -4/5 times 1, which is -1 plus 4/5, which equals -1/5. The inverse will therefore be the matrix 1, 4/5, -1, -1, divided by the determinant -1/5, which means we just multiply by -5, giving us -5, -4, 5, 5. We have found all the components to diagonalize A, those being X, D, and the inverse of X. But in order to show that setting up the matrices in this way does in fact give back A, following the equation A equals X, D, X inverse, let's do the multiplication to verify. First, take D times X inverse, and we get -5, -4, 10, 10. Next, we will multiply X by this new matrix, giving us 5 minus 4/5 times 10, 4 minus 4/5 times 10, -5 plus 10, -4 plus 10. This becomes 5 minus 8, 4 minus 8, 5, 6. We end up with -3, -4, 5, 6, which was indeed the matrix A we started with. Diagonalization helps make computations with matrices much easier and computer-friendly, making it a valuable process to remember. So let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.